reviewing, well, you probably already know all of it, but the classical sampling theory. Okay, and then I'll go into the nitty-gritty details of the sampling signals with finite rate of innovation. What is finite signals with finite rate of innovation? And then, as I mentioned, show two applications that are related to the biomedical engineering. So the usual sampling setup, let me see if I can use this. This usual sampling setup, you have a signal x of t, and it goes through some acquisition device, which usually is a low-pass filter, and we obtain a low-pass approximation of the signal or a filtered signal, and then it gets uniformly sampled. Okay? So the questions that come into play are, when is there a one-to-one map between the samples that you acquired and the original continuous time signal? So are the algorithms efficient? Is it a stable reconstruction? Is it robust to noise? And is the recovery optimal? So these are some of the questions that are of interest to this area. Okay? So for those who studied signal processing in their first year course, we have this classical sampling theorem, which basically states that a signal can be perfectly recovered, a signal which is band limited, meaning that the spectrum has a finite support, or the Fourier transform has a finite support, can be recovered by taking samples, a uniform set of samples, at a distance t. Okay, and the number of samples that you need has to be at least 2 times the maximum frequency, the bandwidth. Okay, so in short. So if we look at it from a system point of view, in the time domain, we have the signal x, a continuous time signal x of t, which gets multiplied by a uniform stream of Diracs, or a comb, right, that is uniformly spaced. And when you multiply these two signals, you're going to get a uniform set of samples. So multiplication in the time domain corresponds to convolution in the frequency domain, and it just so happens that the Fourier transform of the stream of Diracs is also a stream of Diracs, but this time the distance between them is at the sampling interval. Okay, so when you convolve the Fourier transform of the original time domain, the signal x of t, that's x of omega, with the a comb of Diracs, what happens is that the spectrum repeats itself. Okay, so it repeats itself at intervals of the sampling frequency. So then, if we just want to recover the original signal, the spectrum of the original signal, what we do is we just multiply it by a rectangular function, and we regain the spectrum of the original signal. So in the time domain, multiplying by a rectangular function, it corresponds to a convolution with a sinc, because the inverse Fourier transform of a rect is a sinc. And when you do a convolution between the samples and a sinc, that's simply an interpolation, and you recovered your original band-limited signal. Okay, so here we assume that x of t is a band-limited signal. So we're able to recover this band-limited signal. Now, of course, in practice, signals are not always band-limited, so what do? Well, we force it to be band-limited. Okay, so this is what we do. Here we assume that x of t is not band-limited. How do we band-limit it? Well, we convolve it with a sinc. We filter it with a sinc, which has a certain band limit. And then we have y of t, a new signal which is band-limited, and we redo the same procedure. Okay, so we multiply by a stream of a comb of Diracs. Okay, uniform Diracs here, and we're going to get the sample values. But the sample values that you get, when you convolve them with a sinc, well, you're not going to get the perfectly reconstructed signal x of t. What you're going to get is y of t. Okay? But you say, well, let's just take a sinc that gives us, let's just approximate, let's take a sinc that has a very, very large bandwidth, okay? And so that we can have a signal, an approximation which is as close to x of t as possible. Okay, now the thing is, if you take a signal, if you filter it with a sinc that has a very, very large bandwidth, right, so that these two are the same, are approximately equal, what happens is that when you're going to sample it, you have to sample at twice the maximum frequency, right? So that means you have to take a lot of samples. Okay, so we don't want to take a lot of samples. What we want to do is we want to recover x of t, which is non-band limited, with the minimal number of samples, just a sufficient amount. Okay, so this is basically where the signals with finite rate of innovation come into play. We define them as we define the rate of innovation rho as having as the number of degrees of freedom per unit of time. So a signal with finite rate of innovation has a parametric representation and has a finite rho. Okay, so it so happens that a band-limited signal, so for instance a signal band-limited to the interval minus b over 2 and b over 2, in other words the bandwidth is b, is also a signal with finite rate of innovation, because you can perfectly recover it, you can represent it by taking a uniform set of samples, right, that are twice the maximum frequency, right? So B samples will recover that signal. Okay, so here the rate of innovation is 1 over t, which corresponds to B. Okay, and another example is a stream of Dirac pulses. Okay, so here we can represent, if we can represent, or non-uniform B splines, if we can represent a signal x of t by a finite sum of xk, which are the coefficients, and a basis phi of t minus tk. So here the degrees of freedom are xk and tk. If we know what xk and tk is, then we have a perfect representation of x of t. Okay, so how many xk's and tk's are there? There's k, and therefore the rate of innovation in this case is 2k over tau. Here we're assuming that, the interval, the time domain, the time interval is between 0 and tau. Okay, so these are just two analytic examples, but I will explain with a graph, a drawing. So here we have a piecewise linear function, and if we take the first derivative of the piecewise linear function, we have a piecewise constant, and if we take the derivative of the piecewise constant, we're going to get a stream of Diracs which are not uniformly spaced, right? So if we take the derivative of this, we're going to get this signal here. So what is the number of degrees of freedom in this case? Well, it's going to correspond to the 4 locations and the 4 weights. Okay? So in this case, over an interval of tau, there are the rate of innovation is going to be 8 over tau. Okay, so that means that if I can recover this stream of Diracs here, these 8 parameters, I can actually go back and integrate it once and get the piecewise constant, integrate it again and get the piecewise linear, and do this r times if it's an r degree polynomial, right? So the goal here is to recover these 8 values, okay? These 8 parameters. So far, so good? Yeah? Okay. So these are more examples of signals that have a finite rate of innovation. So here we have a bilevel signal which come about in communications, or a piecewise constant signal. A stream of Diracs, as I mentioned, you can see it as a Poisson process or action potentials in biological processes. Piecewise polynomials in 2 dimension, you can see it as a woodcut picture where you carve into wood, and so the edges are very, very sharp. Okay, in biomedical, this is an example of a band-limited plus a piecewise linear signal. So we have electrocardiogram signals. This is actually one of the projects that we've been working on recently, actually with Thierry Bleu also, and how to represent these signals and remove the artifacts. So if you look at these signals, we have a sharp transition, a sharp discontinuity. Okay, these discontinuities are what cause signals to not be band limited. Okay, and actually that cause the spectrum to be infinite. And finally, another example of this is a filtered stream of Dirac. So if you look at all of these signals, they are all sparse in some sense, okay? And they all come down to the stream of Diracs, okay? You can represent all of these signals from the stream of Diracs. So that's why we're going to study the case of sampling and reconstruction, the stream of Diracs. So wait, how do you go? Okay. No. Oops. Okay, so this is the sampling theorem for the periodic stream of Diracs. What it says is that we consider a tau periodic stream of k Diracs with amplitudes xk located at distinct times tk, and this in the interval from 0 to tau. Okay, so tau here is the period. And so you have that x of t is given by this expression here. Okay, so the rate of innovation is going to be 2k over tau. Okay, why 2k? Well, k for the weights and k for the locations. Okay, so the number of parameters that we're looking for is 2k. Okay, if we have these 2k parameters, then we're done. Now, if you take a sampling kernel of bandwidth b, which is greater than the rate of innovation, okay, so here there's no Nyquist. I just want to remind you, there's no Nyquist. We're not talking about band-limited signals. We're talking about signals that are not band-limited. Okay, so the bandwidth, the sampling kernel of the bandwidth has to be greater than the rate of innovation. And so we're going to choose this Dirac kernel, which is a sinc, okay, such that the bandwidth is going to be greater than 2k. Okay, so you need to take sufficient samples, right? That's why we're saying this. So the number of samples that we're going to take, n, has to be greater than b times tau. Okay, so b tau is going to be 2k. And so these samples, you can actually obtain them by taking the inner product of the signal, x of t, and the sampling kernel. And if you calculate all this, it comes down to something like this. Okay, so these samples here are going to be a sufficient characterization of your signal x of t. And that's what I'm going to be showing in the next 5 minutes. Okay, so just to recapitulate, we need n samples, okay? And the number of samples has to be greater than 2k. That's what you need to take note, because you have 2k unknown values. Okay, so let's do this step by step. So we have, sorry, my step by step is too fast. Okay, okay. So we have here a stream of Diracs. Again, the t's are the locations of the Diracs, and the xk's are the weights, okay, of the Diracs. Now here they're all positive, but they don't have to be positive. It's just an illustration. Okay, they can be anything. And you can see that they're not uniformly spaced. These are really distinct, non-uniform spaced Diracs. So we filter them with a filter. We filter them with a function, or we do the convolution with a sinc function. But this phi of t can be anything. It can be a Gaussian. It could be a spline. Okay, there are some other works that have done this. And so when you convolve it, you're going to get your, let's suppose this is a sinc, you're going to get a low-pass approximation. Then you multiply by a uniform stream of Diracs so that you get a uniform set of samples. And these samples, again, are obtained by doing the inner product between the original signal and a shifted version of the filter. Okay? So inner product, as you know, convolution involves an integral, right? So the inner product just comes from that definition. You can easily derive that. Okay. So the first step is to find at least 2k spectral values of x of t. The second step that I'll be showing is that you need to find k annihilating filter coefficients. The third step, you're going to find the k Dirac locations. And then finally, the last step is to find the Dirac weights. And for this, you need to have the Dirac locations and also actually k spectral values. You don't need all the 2k spectral values. Okay, so I'll be going through each one of these steps with you to explain. So let's look at what the periodic stream of Diracs signal looks like. Okay, so here x of t is our stream of Diracs. Now, because it's a periodic signal, we can represent it by its Fourier series. Okay, so here x hat of m are the Fourier series of this signal x of t. Okay, and if we calculate the Fourier series of x of t, we get this expression here. Okay, so what you have to take note here is that this expression is actually a linear combination of complex exponentials. Okay, the whole thing is in this. Okay, so because this is a linear combination of complex exponentials, we're going to be able to find these the locations and the weights. Okay, so here again the rate of innovation is given by k locations and k weights for each period, and therefore 2k over tau. If we take a look at the sinc sampling kernel, so here is a periodized sinc sampling kernel. So this is in the time domain, this is in the frequency domain. Everything here on the outside of minus m to m, outside of minus m and m is 0, right? So you have that the Fourier transform of the sinc is going to be equal to 1 for m between minus m and 0 else. Okay, so the m that we take here is going to be the floor of b tau over 2. Okay, why? So that the b here, so that we have that b is greater than the rate of innovation. So the next step was to find the n samples. So when we filter the signal x of t with that sinc, okay, so the dotted line here is the filtered signal, and then, well, the solid line are the uniform samples. Okay, so as I mentioned, you obtain the samples by filtering or convolving x of t with phi of t, and then taking uniform samples of that. And this corresponds to doing an inner product between x of t and a shifted version of the sinc kernel. Okay, so these are the samples. So you can calculate these samples. But in practice, these samples are given by the acquisition device. Okay. So now we start in the reconstruction. We have to find at least 2k spectral values of xt. Okay, so since the number of samples that we obtained is greater than 2m plus 1, okay, we substitute the signal x of t into this expression, and what we get is a system of equations. Okay, so the system of equations has there's n equations and 2m plus 1 unknown contiguous spectral values x hat of m. Okay, so these are the unknowns here. Yn we know because we acquired them, and x hat of m we don't know. So we need to find the 2k or the 2m plus 1 in this case spectral values. Okay, so if we have if we take k equal to 2 and you take m that is greater than k equal to 2, so let's take m equal to 3, what's going to happen is that you're going to be repeating. Remember what happens when you sample in the time domain and the spectral domain, it gets repeated, right? So this is here are repeats of the middle part. Okay, so we want to be able to recover these spectral values. So here we have y hat of m. This corresponds to the Fourier transform of the sampled signal, right? And we want to recover these 2k spectral values of x of t. Okay, now in certain cases when n is actually divisible, when tau is divisible by the sampling interval, then we actually have what happens is that the spectral values of the sampled signals, or the Fourier transform of the sampled signals, corresponds to the spectral values of the original signal multiplied by a certain parameter tau. Okay, so you can easily recover these. Okay, but if not, you simply have to solve this system of equations here. Okay, to recover these spectral values. Oops. The next step is to find the. So now what we have are 2k spectral values. The next step is to find the k annihilating filter coefficients. And so what is an annihilating filter? Annihilating filter is such that if you convolve it with a signal or a sequence, x hat of m in this case, it's going to give you 0 for all the values. Okay? So it annihilates the signal. So we can easily verify that the filter hm with z transform h of z equal to 1 minus u1z to the power minus 1 can annihilate the exponential sequence x hat of m equal to u1 of m. Okay, so this is just a small example. So if you have a filter, the coefficients here of the filter are 1 and minus u, right? And if we convolve those coefficients with a signal x of m, x hat of m, sorry, then we can easily find that its convolution is going to be equal to 0. Okay, so we can actually verify this. We can actually generalize this. We say that a filter with coefficients hm whose z transform is given by the following, which is the product of, which can be expressed as the product as its zeros, right? As the product of 1 minus ukz to the minus 1, can annihilate the linear combination of exponentials given by this expression here. Okay? So here the uk's are simply, for purposes of notation, we simply use, we simplify the uk to be e to the minus I 2 pi tk over tau. Actually, uk equal to e to the minus I 2 pi tk over tau is what corresponds to our Fourier series, right? So you can verify this as well, that these coefficients here are actually going to annihilate this, the spectral values here. So the question is, how do we find these two, the annihilating filter coefficients? Well, we can use the 2K spectral values and then solve the Toeplitz system of equations. Okay, so let's just take an example here. If we take k equal to 3 and you let h naught equal to 1, then we can just write out these equations in a matrix form, and this actually corresponds to Toeplitz system of equations. If you recall, what is a Toeplitz system of equations is one where the diagonals are the same. Okay? Sorry, this thing is... Okay. So the diagonals are the same. So this is a Toeplitz system of equations, and we simply solve the system, and we solve it for h1, h2, h3, which actually corresponds to our annihilating filter coefficients. Okay, so here, if you look at the components of the matrix of the Toeplitz system, they're actually the spectral values. And remember, we already got 2K spectral values. Okay, so we can easily find this system of equations. So finally, step 3, we want to find the K locations of the Dirac. So if we have those filter coefficients, right, then what do we need to do? What we need to do is we need to simply find the roots of the Z transform of the annihilating filter. Okay, so this is the annihilating filter. We find the roots of the Z transform, and the roots of the Z transform are going to actually give you UK, right? And UK gives you the TKs. Okay, so from the UK, from the roots, you can actually find the K locations of the Diracs. Are there any questions so far? No. Okay, so this is actually a nonlinear problem, and you can see that the annihilating filter is similar to the error locator polynomial in error correction coding, or in Prony's method in spectral estimation. Okay, it's a similar concept. Finally, we want to find the K weights of the Diracs. So right now, what do we have? We have 2K spectral values. We have the K locations, right? So we have n samples that led us to 2K spectral values, that led us to the K locations, and now we're looking for the K weights of the Diracs. Okay, so from the K spectral values and the K distinct locations, we can actually go back to the expression of the Fourier series, right? And if we write out this system here for k equal to 3 again, right, what we see is that this actually forms a van der Waals system of equations. So for those who don't remember, a van der Waals system, a van der Waals matrix is one where the rows are powers of each other. Okay? So this second row here is a power of the first, and it's a power of 3 of the first, a power of the second. Okay? Just to explain. So
usually the first row is all 1 in the van der Waals.
Yeah, but it doesn't matter.
You're missing constants.
Yeah, but it doesn't.
1, 1, 1.
Yeah.
And so on.
Yeah, but it doesn't matter in this case. I mean,
You can factor out the first columns that you use. Typically, it has 1.
Yeah, it's to the power of 0.
Yeah, because it's 1x, x squared, and so on.
Yeah. So here you're in the traditional van der Waals, you want.
Yeah, but the van der Waals has one of the rows or columns identically 1.
To the power of 0. Yeah. Yeah. So in this case, well, we can. Okay. The advantage of the van der Waals is that it admits a unique solution when the values along the rows are distinct, right? So in this case, because the UKs are related to the TKs and the locations of the Diracs, well, they are distinct. Okay. So we have a solution to this. So this comes down to solving a linear problem, okay, and so we're done, actually. Okay, so if we look at the complexity of the FRI sampling and reconstruction scheme, what we have is that we needed to find n samples which are obtained from the analog to digital converter, the acquisition device. The 2K spectral values from the discrete Fourier transform of the samples can be obtained in operations of the order of k log k. And the k annihilating filter coefficients, you need to obtain them from the Toeplitz system. So these are all polynomial in k. Okay, all these operations. So this is k squared. And the k locations from the roots of z transform of the annihilating filter is a nonlinear problem. So it's in the order of k cubed. And the k weights from the van der Waals system, which is a linear problem, can be obtained in computing operations in the order of k squared. Okay, so here the key to the solution is that we can separate the nonlinear from the linear. Okay, in this problem here. So finding the locations is of these Diracs comes about in many other problems, such as retrieval of sparse signals, but also in registration and feature detection, etc. Okay, so registration, there is one example that I won't be showing, but for super resolution, you want to do super resolution, you need to register the images. Okay, so they have applied this technique for that. Are there any questions so far?
Do you consider noise data?
Yes, actually.
In that case, it's not easy to find the location of Diracs in noise data.
Yeah, I'll just say a few words on that. So there are other sampling kernels, as I mentioned earlier. You have the sinc, besides the sinc, you have the Gaussian and the splines. Okay, so this was in our paper in 2002. And also some other extensions on 2D what has been investigated. And the noisy case, which Thierry is actually the master of, Thierry Bleu, here, for example, we have we can have different types of noise, right? You have analog noise and digital noise. So in this case, if we look at an example of ultra-wideband communication signal, okay, the red line is actually the signal and the blue is the noise. Okay, so then it becomes a very, very hard problem, right? So I won't be showing the results on this, but you can find it in this paper, 2008. Okay, so how they go about to resolve it is when we take the samples, okay, we apply again the fast Fourier transform, and if these samples here are too noisy, there's a Katza iterative method that is applied, okay, which basically allows you to do the denoising. Okay, so what happens is that when you have a Toeplitz matrix, remember the Toeplitz matrix, right? Because of the noise, the Toeplitz matrix won't be, you won't have that all the diagonals are the same. Well, it won't be Toeplitz, in other words. Okay, so what you do is you make it Toeplitz, so you take an average of the diagonals and you iterate in this way. Okay. Okay, so now in the second part of this presentation, I'll be just presenting two examples of two biomedical applications. Okay, the first one is where we wanted to, okay, the initial problem was to detect seizures in neonates. Okay, so when you have, seizures are epileptic seizures. Okay, so when you have when an adult has an epileptic crisis or fit, they react, you see a physical reaction. But for babies, for newborns, it all happens in the head. So what you need to do is you need to analyze the electroencephalogram, okay? And so the idea was to see if we can make use, and so you have a lot of data, okay? You have a lot of data because you need to monitor them for 24 hours and days at a time. And so you're gonna have a lot of data to analyze, and so what the objective or the goal was to be able to model these neonatal EEG seizure signals or signals, and to see how you can use the FRI concepts to actually find the seizures. Okay, so this is the work, some of the work of one of my PhD students who now graduated. And the next example I will be showing is on diffusion magnetic resonance imaging, which is actually current work of one of my current PhD students. Okay, so let's look at a section of the neonatal EEG seizure signal. It looks something like this. Okay, now if we're able to extract, this second figure is an extracted stream of Dirac pulses. Okay, so we actually can differentiate this and find a way to get the most important stream of Dirac pulses. Then if we integrate this twice, we're going to get this non-uniform linear spline approximation of the seizure signal. Okay, so here, how do we apply the FRI scheme for the non-uniform linear spline? Well, here I assume that it's a non-uniform linear spline, so a degree spline of 1. Okay, and what I need to do is, again, this is a sampling procedure. I filter with a sinc, I sample it, and then I get a uniform set of samples. Then I have to find, it's the same as previous, I find the 2K spectral values of the original signal. Okay, now because the 2K spectral values of the original signal, I can't really do anything with that, right? I need to find the spectral values of the stream of Diracs in order to apply my scheme, right? So I know that I can differentiate r plus 1 times, in this case twice, I know that there's an expression for the spectral values of the, let's call it the piecewise linear here, or the non-uniform linear spline, in terms of the Diracs, right? So here what I obtain, if I differentiate this r plus 1 times, I can obtain the spectral values of the Diracs. So once I have the spectral values of the Diracs, I simply apply the annihilating filter. I find the K locations, and I find the K weights, and then I simply integrate twice, in this case, and I recovered my uniform linear spline. Okay, so here are some close-ups of the reconstruction of the neonatal EEG seizure signal that I showed earlier. So we have in light blue, which you barely see, the actual seizure signal. So you have it right here. Okay, and if we were to use the traditional Shannon sampling theorem or the Nyquist sampling theorem and simply, sample the low-pass approximation, what you would get is the dashed black line, okay? Which is not bad, right? Except that for biomedical signals, okay, the morphology is very important for the doctor. Okay, so for the doctor, this would not be good enough. Okay, so with the FRI method, or by modeling it as a non-uniform linear spline, we're actually able to have a good representation of the seizure signal. Okay, so this brings me to my second application. So diffusion weighted magnetic resonance imaging is the only non-invasive technology that can image the fiber tracts in the brain. Okay, and so we want to be able to find out if we can use FRI to actually find the fiber orientations. Okay, so this actually leads to a connectivity. By being able to track these fibers, it will lead to a connectivity map. Okay, so what has been shown in the literature is that we can model these DMRI signals as a spherical convolution between the fiber orientation density function and the response function of one fiber. Okay, so here we have this type of model. Okay, so if you have a visual example, here we have the fiber orientation density function. Here, and this is the DMRI signal. Okay, so we want to be able to recover. Okay, so if we have a model and we model the directions here, theta k and phi of k of the signal by this expression, we want to be able to find these theta k's and these phi k's in this example. Okay, so how do we put it in the framework of FRI? Well, this is the fiber ODF signal that we modeled as a stream of Diracs, and we simply do a spherical convolution with r theta, and this is going to give you something on a sphere. And so you're going to sample this on a sphere, and then by using the samples that you obtain, you can use the FRI methods to recover these locations, or these directions, I should say. Okay, so in a noiseless setting, an ideal R theta, meaning a sort of low pass kernel, we can actually recover it using n, which is number of samples n equal to 3k. Okay, so I won't be showing the results of this because it's still work in progress, although we have a paper that has been accepted for conference that is coming up in September at the EMBC in San Diego. Okay, so if you're interested in learning more about this, you have some nice theoretical papers that have been presented in the past, that have been published in the past, and this is the most recent work on my side. But there are other people also working on biomedical applications. Actually, Thierry also worked on EEG source localization of seizures, right? Yeah. So there are some other papers on this as well. Okay, so thank you.
Yeah, any questions or comments?